Yes, sir.
Okay, thank you. So just giving you the recap what I have discussed last time. Class के बाद में things. So just giving you the little bit recap whatever the things I have discussed last time. That before last class I have discussed about the sequence spectrum techniques. What is this? That is the amplitude of second type modulation of the BPSK signal, and then we have seen that how can we modulate it, how can we demodulate it. Then we have seen the effect of the noise in direct sequence spectrum techniques, and in the first case we have considered the thermal noise. There we have seen the probability of error for this direct sequence spectrum technique is similar to that of the BPSK. Now in the second case we have considered the uh, single tone interference and jamming, and we have taken the same block diagram where we have changed the characteristics of the noise by single tone interference and jamming signal, like single sinusoidal signals we have seen. And then we had calculated the probability of error. So how did we calculate the probability of error? We have calculated the probability of error just by first finding out the power spectral density, and then replacing that, equating that by eta by 2, and then we have taken the same formula what is being used for the BPSK signals to find out the probability of error. So for that we have taken the noise as a single pole interference, that is under 2 pj cos omega naught t plus theta, and then the receiver, the signal at this point will be how much under 2 ps gt gt. This is nothing but the DSS, direct sequence spread spectrum, and then under 2 pj cos omega naught t, that is nothing but the noise. And then we have seen that once this received signal gets multiplied by GTN, again multiplied by under 2 cos omega naught t, and passes through the integrator end of circuit, then what will be the output? So before passing through the integrator end of circuit, we have seen that after multiplication of these two, we can we can finally write this expression by this one. And then once it passes through the low pass filter, we can only take at the output to the lower frequency component. That is, we can ignore this, we can ignore this, we can ignore this term, and only the remainings are this and this. So we can write it as under PSTT this, and then under PSCT under PJGT cos theta. Then here we have seen that in the initially at the starting our massive signal was spread, whereas there was no effect on the noise, because there is no multiplication of the GT, and because of the multiplication of GT itself there is a spreading. But at the output we have seen that we have the data signal as it is, but the noise signal gets spread. So considering these noise signals, we have calculated the probability density functions, because we know that this noise signal is having the term of GT, which is nothing but NRZ, and we know the power spectral density of NRZ, which is given by sinc square functions, and by changing the amplitude portion of that, we have calculated the probability density functions. And then since this f is much if f is much less than fb, bit rate of the message signals, then we can make it as a constant, and we can approximate this probability density functions by the constant functions. And since cos bar is cos theta is nothing but the half, so we have replaced that by half, and then we have calculated the probability the probability density functions, and then we have calculated eta, then we have put the value of eta in this particular equations, that is the probability of error, which is valid for DSS, or we can say for the BPSK system. So the probability of error is just like just by increasing this processing gain, or we can say just by increasing the chip rate of the gain sequence. So this one was our conclusion which we have drawn, and this factor Pj effective, which was Pj divided by 2 Fc by Fd, is called as effective jamming power. So if our chip rate will be high, then processing gain will be high, and effective jamming power will be low. And if this effective jamming power will be low, then this factor will be high, and since complementary error function is decreasing functions, so that will be low. Now, then I have discussed about the pseudo noise code, and first I had discussed about the basic property, that is this one is not the In strict sense, it is a deterministic signal, whereas since the period of the repetition is very large, so in our practical purposes, we simply consider as a random code. Random code. And how can we generate this random code? That also we have learned. That is just by using shift registers and number of shift registers, and you can say the number of flip-flops and exclusive or logic circuitry. We can generate the PM code. And in fact, at the starting for the better understanding, we have taken the 3 numbers of flip-flop or shift registers and 1 number of exclusive or logic circuitry. And we used to get the PN sequence at the flip-flop number 3. Okay, this is the output. And whenever the clock will appear, whatever the bit will be there in the shift register 1, 2, or 3, that will be shifting 1 bit ahead or 1 shift register ahead. That is 1 will go to the 2, 2 will go to the 3, and 3 output and whatever the bit will be stored in the 1, both will be XOR, and that output will be given to the input of the first shift register, and then for the equal shift. So if we starting at the starting, if we assume that our shift registers store the 1 bit, then in the first clock, this 1 will shift to the 3 and this 1 will shift to the 2. That 2 will go to the 3 and 1 will go to the 2, and 1 bit and the output of the 3 will be XOR. So since 1 are there, so once we take the same number of bits, since XOR is represented as AB bar plus BA bar, so if there are same bits, then that is if A and B both are same, then the output is nothing but the 0. If A and B both are different, then output is nothing but 1. So that's why at the shift register 1, 0 is stored. Now in the next clock, this 1 will shift over here, this 0 will shift to the shift register 2, and 1, 0, since both are different at the shift register 1 and 3. So 1 will be stored in the shift register 1. Similarly, this 0 will move to the shift in the third shift register, 1 will move to the second shift registers in the next clock. And then since both are same, so 0 will store in the shift register 1. The same process will be repeated. 0, 0 same, so 0 will be stored in 1. So 0, 0, 0, 1 different, so 1 will be stored. Now this will go to here, this will go to here, 1, 0 different, so 1 will be stored. But after this, 1 will go here, 1 will go here, and the combination of these two will be 1. So the same bit is repeated. And since we are taking the output from the shift register 3, so the output of the PN generator will be nothing but 1, 1, 1, 0, 1, 0, 0. So this is 1, 1, 1, 0, 1, 0, 0. So you can see total 7 bits are received, or you can say 7 chips are received. So we call it as total 7 chip maximal sequence code. Why we call it as maximal sequence code? Because if that generator which produces the n which is given by 2 to the power n minus 1, where n is the total number of flip-flops or shift registers, then that is called as maximal sequence code, which we might have already studied in your ITC, or if you have not gone through that subject, then you will be studying in your higher subject. I don't know actually exactly remember that in which semester you have that particular course, that is information theory code. So n equals to 2 to the power n minus 1, where n is the total maximum number of chips. So in the graphical form, if we use to represent it in the NRZ form, convert it to 0, then 1 is represented by plus report and 0 is represented by minus report. So it can be written in this. Now suppose, but here you can see, since this one is generated in the deterministic way, and in fact the number of this number of electronic circuitry is less, so you can simply say that after this 7 chip, the same data will be repeated, because in the next clock you can see 0, 1, 1 and 0, 1, 1 is over here also. So the same bit is getting repeated. So we cannot say that this sequence is random in nature, because the pattern is known. That is after 7 chip, it is going to be repeated. So but if you take the large number of these shift registers and this XOR gates, then what happens? These repetitions may be after a long chip sequence. So that we can consider that is it is not having any particular pattern, because once you look to this, you will not find any similar. That is here 1 1 1 0 1 0. So there is no such similarity between the patterns. So you can say that it is purely random in nature. So, and if you talk about the various properties of the pseudonoise, in fact, some properties I have already discussed last time. But if you talk about the some, so going through the same properties, then if you see that number of ones in this one are 1, 2, 3, 4, whereas number of zeros are 3. So whatever the circuit will be using, you will be getting the one more number of either 1 or 0. So for this particular circuit, you will always be getting the one more number of ones as compared to the number of zeros. And if you take, suppose if you take the output to a target, input to a target from this sequence 2, then output of that, whatever the bit chip will be getting, that is called as mirror image of this. And in that particular case, we'll be getting the one more number of zeros as compared to the number of ones. And looking to some mathematical explanations, like if the clock speed is given by RCH, then at each clock, since we get the output, so definitely this chip duration TCH, this is the chip duration TCH. TCH is determined on the basis of clock speed, and that is inversely proportional to that 1 upon RCH. If CT is the periodic, CT is nothing but the pseudonoise random code. Earlier I used this by GT, but I think you can consider it as CT, or you can consider it as CT. Just the difference in the we are the representation. So here, if you represent the CT is periodic, in that each period of the repetition of a given sequence of n chips, okay, the sequence itself exhibits random properties, which will be described shortly. The periodic time of the waveform is given by how much? Periodic time of the waveform is given by, suppose there are n number of chips. So if you multiply n by TCS, then that will be the period of the whole waveform. So n into TCS. That is, after that much of period of the time, the same sequence will be repeated. Okay. Now, all these things I have already discussed. I have already told you. Move to the next. That is, such codes are known as the maximal sequences or M-sequence code, because they utilize the maximal length sequence that can be generated, and it uses the n equals to 2 to the power n minus 1, where n is the total number of shift registers. Okay. All these things are written so that once I share this PPT, you can, if something you missed out, then you can simply recall it, just go through it. Now, similarly, the binary ones and zeros are randomly distributed such that the code exhibit noise-like property. And since we know that noise is nothing but the random in nature, so we call it as pseudo-noise, although it is not purely random in nature. However, there are certain deterministic features described here, which I'm going to describe, whereas first I've already described, that is the number of binary 1. Number of binary 1 is given by 2 to the power n by 2, where n is the total number of shift registers. So if suppose in this particular case n equals to 3, that is 2 to the power 3 by 2, which is the number 4. Okay, let's say we are getting the 1, 2, 3, 4 number of zeros, and definitely the number of 4 number of ones. Similarly, the number of zeros will be 1 less as compared to the number of ones. So if the number of ones is 2 to the power n by 2 by 2, then the number of zeros will be 2 to the power n by 2 minus 1. So similarly, you can see as output of the flip-flop 3 consists 3 zeros or n equals to 3. And one more thing here I want to point it out, that since number of 1 or 0 differ by 1 only. So what happens? Since if you represent this PN sequence by NRJ data, then this one will cancel, this area will cancel out this area will cancel out by say this, and this area will cancel out by say this. Only this area is remaining, and whatever the DC term will be getting, that is only because of this area, or in the opposite sense, only because of this area. And if this number of bits are large, then the DC level becomes small, because DC level is ultimately given as V by N, total number of chips. So if the period of the repetition is very large, so definitely there will be large number of chips, and then the DC level VR by N will be low. So this is another unique property of the PN sequence, that is, it is having the negligible DC level, which is given by VR by N. So the importance of this relationship is that when the code uses keyboard for the binary 1 and binary keyboard for 0, the DC board is close to 0. Close to 0. However, since ones and zeros differ by 1, so definitely there will be some small amount of the DC level. And but that depends upon the how many chips are being used, how many chips are generated before the reputations. So that decides that how much that DC level is close to 0. And for any communications, this DC level should be as low as possible. While discussing the concept of signaling, I have already told you. We prefer because at some times, like in the repeaters itself, we used to use the transformer. Where if there is a DC signal, then the coupling of the DC signals with the transformer bindings are possible, which is not actually required. And then this, as I told you, the DC offset is given by V by N. This VR I have taken to this V only. So no problem, that this DC offset is given by V by N, and this since N is the chip number of chips generated before the repetition, so definitely this DC offset is very close to the 0, or you can say very less, very low. Moving to the next property, up to here I have already discussed, but I wanted to give you the recap, whatever the things I have discussed last time. Now, moving to the next property, number of maximal sequences. What is the meaning of the total number of maximal sequences that can be generated by n state shift registers, and its associated logic circuit is given by, what is this? The total number of maximal sequences that I want to say that here, I suppose if you are using the 3 numbers of shift registers, then you need one configuration you can use this one, and another configuration you can use the mirror image, and that is mirror code, that is once the input of this XOR is taken from the 2. It means that in this particular arrangement, once we take the 3 flip-flop, two maximal sequences are possible. Okay, like this may be the pattern 1 1 1 0 1 0 0. In another sequence, there may be the 4 number of zeros and 3 number of ones. So there are 2 maximal sequences are possible, but this we can guess if you have the less number of circuit, like less number of flip-flop, like in this particular example we have taken 3. But if the number of flip-flops are large, like n, say number of flip-flops are large, that is given by n, and this n is large. So how can you calculate that how many number of total maximal sequences are possible over here? So that we want to calculate. In these properties, that is the total number of maximal sequences that can be generated by an n state shift registers. Like in this particular, in the earlier case, this n was 3, and we have seen that 2 maximal sequences, 2, not 3. That 2 maximal sequences are possible. Okay. Similarly, if there are n, if n is large, then how can you calculate that total number of maximal sequences? How can you calculate? So that is calculated by this formula. That is S max. That is S max is nothing but the total number of maximal sequences, possible maximal sequences, which is given by phi n by n. So you might be thinking that what is phi, what is n, and even knowing n is nothing but 2 to the power n minus 1, where n is what? N is nothing but total number of shift registers. So this n is total number of shift registers. Capital N is 2 to the power n minus 1. S max we can calculate, but until unless we don't know what is phi. So let us see what is phi. So phi is nothing but Euler functions. Phi n is known as Euler functions. So how can you calculate the value of these Euler functions? If you are able to calculate the value of these Euler functions, and this n is known, we can calculate this S max, and that you can say that much number of maximal sequences are possible. So this phi n is known as Euler functions, which gives the number of integers in the range 0, 1, 2, 3 up to n minus 1. That is, this phi n can take the value in integer which can range from 1, 2, 3 up to n minus 1. Like suppose if we have the 3 flip-flop, then n will be 2 to the power 3 minus 1, like 7. So that phi n can take the value from 1, 2 up to 7, and that are relatively prime to n. That are relatively prime to n. So you might be thinking that you might have heard the name of prime numbers, but you might have not heard the name of relatively prime to n. So the meaning of relatively prime to n is that the two numbers are relatively prime. When two numbers are called as relatively prime, two numbers are relatively prime when their greatest common divisor is 1. A general formula for finding this phi n. General formula for finding this phi n is given by n p1 minus 1 by p2 and so on pr minus 1 by pr. So you might be thinking what is pn, what is pr, like that. So this p1, p2, pr are the prime factor of n. So this is that if you know that what are the various prime factor of n, prime factor of n, so that prime factor will give you the value of p1, p2, p3, pr. Suppose there are 3 prime factors of n, then the p1, p2, p3, 3 p's we need to calculate or consider. And correspondingly, we can calculate phi n by putting in this formula, and then phi n taking this in this equations, you can calculate the total number of maximal sequences. So you might be thinking so for that, let us take an example. That is, for example, if we take n equals to 8, that is, there are 8 number of flip-flops or shift registers. Then capital N will be 2 to the power n minus 1, that is 2 to the power minus 1, that is 255. 255. Now, if you calculate the prime factors of 255, then those prime factors are 3, 5, 17. So, if you calculate the prime factors of n, that is 255, then the prime factors of 255 are 3, 5, and 70. Okay. Now, hence, this P1 we can take as 3, P2 we can take as 5, and P3 we can take as 7. And we can calculate 5 to 55, but we have n is to 55, so we can write it as 5 to 55, which will be n to 55, then 3 minus 1, 2 divided by 3, 3 minus 1, 2 divided by 3. In the next, P2 is nothing but 5, so that will be 5 minus 1 divided by 5, that is 4 by 5, and P3 is nothing but 17. So 17 minus 1 divided by 17 minus 1, that is 16 divided by 17, and it will come out to 128. Now, the S max how can we calculate? 128, which is the value of 5 to 255, divided by n, where n is nothing but 8. Small n is nothing but 8. So if we divide this 128 by 8, we will be getting 16. That is 16 numbers of total maximal sequences are possible. Maximum number of sequences are possible. Okay. Now, if we take a little bit simpler example, which I told you earlier also, that is, in somewhat simpler examples, consider the case for n equals to 3. If we take n equals to 3, which is in fact in the previous example what I have taken for this particular circuit. For this circuit. Since here we have taken n equals to 3. Okay. So if we consider this, and we have seen that there are two maximal sequences that are possible. So if you take n equals to 3, okay, capital N will be 2 to the power 3 minus 1, that is 7. And if you calculate the prime factor of this 7, then that will be nothing but 7 itself. Only one prime factor is there for 7, that is 7 itself. And hence that we can consider as a P1. So P1 is 7. So we can calculate 5, and capital N is how much? 7. So if we calculate 5, 7, then we'll be getting, so we will be getting n is 7, then 7 minus 1, 6 divided by 7, which is nothing but 7. And then S max will be how much? 6 divided by n is 3. So 6 divided by 3 is nothing but 2. And we have already seen that in this particular case, there are only two distinct maximal sequences, which I told you that one, what we have mentioned in this particular table, and another is nothing but the optimized code. So there are two possible maximal sequences are there. This is the second property we can say for the PN sequence. So all this property, if you look to all this property, it does not tell you that all these properties are of a random sequence. All these properties are of deterministic sequence. Third one, which is the most important, which is most commonly used in the auto-correlation functions, most commonly used in the communication system to find out the similarity between the city and similarity between the city and the shifted version of that city that is given by the auto-correlation functions. So all of you are knowing this auto-correlation function is used to find out the similarity between the signal and the shifted version, time shifted version of that signal. So the property of this city, that is, if that city is the PN sequence, then it is the autocorrelation function of that. So this autocorrelation function of that city is high if the time lag, that is time lag or time advance becomes 0. So because if both the signals are very much close to each other, then only the autocorrelation function gets maximum value. So that one of the most important property of the city is its autocorrelation function. And in fact, this autocorrelation functions concept I will be using in one of the applications of the DSS. That is how to find out the range of a using target using direct sequence spread spectrum. So one of the applications I will be discussing considering this also. So there we will be using this concept of this property that the PN sequence, that is autocorrelation function. So move to that. The autocorrelation function is a measure of how well a time-shifted version of the waveform compares with the unshifted version. Okay. So this all of you knowing that this I have already discussed in the probability of random process, and you might have already studied in the ACS also. So autocorrelation function. So the figure A, like this figure, shows the autocorrelation function of the city. That is how can we calculate. So city autocorrelation functions, you are knowing that integrations over 0 to say TC or LTC, that is the number of chips, and if the TC is the chip duration, then at least in one period we need to integrate. So integrations over 0 to LTC, then CT, and the shifted version, multiplication of the CT and the shifted version of that CT, that is CT into CT minus tau d tau. dt, CT into CT minus tau dt. So since we integrate that with respect to time t, so ultimately the resultant value after this integrations will be the function of tau only, will be the function of tau only. So how can we calculate the autocorrelation functions for the PN sequence? And in fact, this block diagram is valid not only for the this one PN sequence to find out the autocorrelation function, but for any sequence you can use this block only to find out the autocorrelation function. That is, we have the city, and here we have the time shifted version of the city. So here we get at this point we get CT into C t minus tau. Now, when this passes through the integrator, we get 0 to say LTC, and then CT and C t minus tau d tau dt. So ultimately, the resultant functions will be getting that will be the function of tau. So here I have drawn the graph in between tau and the output of these autocorrelation functions, and here you can see that this tau is 0. Once this tau is 0, that is, once this CT and CT minus tau both are same, because once this tau will be 0, this CT and this CT t minus tau both will be same, and in that case we can say that there is a maximum similarity. In effect, the autocorrelation function stays as the same. That is, we are getting the maximum value of the autocorrelation functions for 0 time lag or 0 time advance or t equals to 0. But if we increase this tau, then ultimately, since the CT and CT minus tau differs by some amount, so definitely the value of the integrations will decrease, and it decreases. The autocorrelation functions value decreases. Okay, and once it is very much close to that of the TCH, then it goes to the negative side. That is, at that time, it gives us the maximum dissimilarity. Okay. So this is how we can obtain the autocorrelation functions for the PN sequence, and that actually gives us the idea that it is having anyhow it is having some correlations. If it would have been the random sequence, then you would have not get the large value of the autocorrelation functions. So any shift in time, advance or delay, as I told you, Away from tau equals to 0 positions will result in a decrease in the output voltage because there the dissimilarity increases. But if this tau is 0, then that will have the maximum similarity because the CT and CT minus tau in that case will remain same, will be same. And for that, the autocorrelation functions, whatever we get, that is maximum. So the property of M sequence code waveform is that the autocorrelation functions decreases linearly from the maximum value until unity in this case, because it is, if we normalize this, then we can divide the whole value by n. So the peak value will be 1 and the slope will be varying in by 1 by n. The very pronounced peak in the autocorrelation functions provides the chief means of acquiring acquisition and tracking. As I told you, like suppose we have any DSS system. There we use the GT, that is the PLC pins. Now some target is moving in the sky, and then if you want to find out the range of this target using this technique, then you need to send the signals, and then the reflected signals you need to receive, and then this time period you can measure. Okay, in fact this time period also you need to find it out, and then if this signal is received, okay, then to verify that whether the transmitted signal is only received after reflections from the target, or some noise signals are received, or some another signals are received in this reverse. Here at the receiving side, we simply make the correlation with the transmitted signal with the received signals. So if this received signal is not distorted much, and so definitely this received signal will be some time shifted version of the transmitted signal. This received signal will be some time shifted version of this transmitted signals. So they are just by adjusting something, that some delay in this GT, adjusting some delay in GT. Suppose this signal is received, this one is T1 time, this one is T2 time, then this signal will be received after T minus T1 minus T2. After T1 plus T2 time, it will be received. Now suppose if we have here some adjustment, delay adjustment, then we can delay this GT by T minus T. Now this delay with the GT minus T, and this signal is given input to this correlator. Then what happen? One is the received signal, which is reflected from the this one target, and another is the original GT what we have transmitted, what we have used in the generation of DSS. There we are intentionally making the delay, and then we observe the autocorrelation functions at the output, and we see that at what point this autocorrelation function is maximum. So since hello. Hello. Harshvardhan?
Yes, sir.
Okay, actually, my Bluetooth device got disconnected. I will connect it.
Okay, it's connected.
Okay. I think it is. I'm audible, right?
Yes, sir.
Okay. There's something I have written that is deleted. So I was talking that this is the DS sequence, and like suppose here this is the DS sequence, and here GT is being used as a PL sequence, which is being used to find out the target range. So from here this signal is transmitted, and after t equals to t1 plus t2 second, like suppose for uh, to and fro, total time is taken as t1 plus t2, and it is being received. And this signal, and after delay to the original GT, say by amount of d, is given to the correlator. This correlator. So if it is given to the correlator, what happens? Since this t is adjustable, and we know that how much the delay we have created in this GT. So this signal will be GT minus d. Then we see that at what point of for what value of d, this autocorrelation function is getting maximum, and that D we are calculating. And since if you are suppose that value of the distance, this D is known. So this D, when this autocorrelation function should be maximum, when this D will become equal to the T1 plus T2, because ultimately this signal will be received as T minus T1 minus T2, and this signal is given as T minus D. So once this T is equal to T1 plus T2, in that case only, as I told you that for tau equals to 0, we will be getting the maximum autocorrelation functions value. So once this T is equal to T1 plus T2, at that point we will be getting the maximum autocorrelation value, and considering that T, and we know that any signals once we transmit it in the free space, that travels, if that one is the electromagnetic signal, so high frequency signals, so travels with the speed of the light approximately c. So knowing the speed of the signals and knowing the time delay, that is how much time it is taking to go and to come, and it is 2 and 4 time, that is d we know. So from that we can calculate the range of that target. Okay, so this is this applications I will be discussing later on, but here I wanted to give you the basic idea about the applications. That is the great applications of this autocorrelation function. Okay, so these are the some important properties of the PN sequence. So end of the PN sequence. Now, so in PN sequence, what are the various things which we have studied? That is, how can we generate the P? I don't know from where some noise is coming from outside. In the PN sequence, we have seen that how can we generate the PN sequence, what is PN sequence, what is maximum length sequence, and what are the various properties of the PN sequence. And most important property, that is the correlation features we have. Moving to the next, our next topic is spread spectrum and code division multiple access, that is called as CDM. Now, so this I will not be able to complete by today, because two or three slides are there for this particular topic, and we have 10 minutes are left. But no problem. Up to whatever the things I will be discussing, that again I will be discussing in the next class, just to recall all those things to complete whole this particular topic. So this you can see, spread spectrum is nothing. What we have studied, and code division multiple access. So this term you might be listening first time. I'm not sure that earlier you have already studied, but no problem. Since here what I'm going to tell you, that is, this is nothing. This CDMA is nothing but an application of this is nothing but an application of direct sequence spread spectrum, what we have studied. So now, if we talk about the direct sequence spread spectrum, then in direct sequence spread spectrum, all things we have studied. That is, what is this DSSS? What are the various characteristics of the direct sequence spread spectrum? How can we generate this direct sequence spread spectrum? How can we detect the direct sequence spread spectrum? And what is the actually characteristics of the direct sequence spread spectrum in the presence of thermal noise and in the presence of single pole interference and jamming? All those things we have studied. Now we are going to study the applications of direct sequence spread spectrum. So here in the coming slides we will be calculating two applications. That is one which is very important, that is called as CDMA, code division multiple access. Because if you recall the basic characteristics of the spread spectrum, then there one point I have written, that is the multiple access technique is possible. That is, multiple access techniques we can actually do multiple access coding techniques we can develop with the help of spread spectrum. There we can transmit the large numbers of users data at the same time using the same frequency band. That is called as CDM, code division multiple access. Large number of user data, that is n numbers of user data, we can transmit using the same frequency band and at the same times. But we cannot transmit with a large number of users data in the same frequency band and same at the same time, because there will be the interference, definitely. Then how can we transmit? By using the different code, by using the different code. That is called as code division multiple access techniques. Okay, so this is the one of the application of DComm spread spectrum, and the second applications, the last slide what I told you, that is to find out the range of a target. So that is the second applications. So both the applications I will be discussing for the DComm spread spectrum. So now, before going to discuss the CDM, you should know that what is the multiple access techniques and what is the CDM. What are the other types of, what are the other, sorry, what are the other multiple access techniques? Okay, so to understand that, let us consider the three axes. Suppose this axis is code, this axis is time, this axis is frequency, right? Mainly, if you talk about the satellite communication, suppose this we have the satellite. Suppose this we have the satellite. So in the satellite communication, what happens? What happens? If suppose large number of users are there at the transmitter, and large numbers of users are there at the receiver side. So to better utilize the resources of the satellite, to better utilize the resources of the satellite, what we do, we find out the arrangement such that the large number of users can transmit through the satellite to the large number of receiving users. So for that we use the multiple access techniques. So how can they do the communications with the satellite to the various users spread all over the world? So for that we use the multiple access techniques. Okay, that is the multiple access techniques. What we do? So there are, so what happens? Or at least one parameters out of code, time and frequency we need to make it different, so that receiver can determine on the basis of that which transmitter has transmitted that information, just to discriminate the various transmitters by the receivers. And these receivers may also be the transmitter, and this transmitter may also be the receiver in duplex type of communications. There is no such issue, but I'm just considering one way. So how at least one parameter should be there which can discriminate that this and nth number of transmitter has transmitted this information. So at that, if user uses the same frequency band, if user transmitters use the same frequency band and same code, but they transmit the information in the different time slot. Like suppose someone is transmitting say 1 second, someone is transmitting after 1.0000001 second, another is transmitting after slightly more than that time. Then the receivers may detect that okay, since they have used that much of time slot, and each transmitter are allocated a unique time slot in the time frame at the satellite. So they can actually transmit in that time slot only, and by sending the and utilizing that time slot, receivers can detect that okay, that transmitter has transmitted this information. So that type of multiple access techniques is called as TDMA, time division multiple access techniques, where user uses the same frequency band and uses the same code. They might have not used the code. They might have used the encryption type of code just to secure the information. But they transmit over the different time slots. That multiple access technique is called as TTM, time division multiple access techniques. In the second way, that all the transmitters transmit the information at the same time, but over the different frequency band. Uses the same code. That is called as frequency division multiple access techniques. In the third, that is they transmit, as I told you in the basic definition of the CDMA, that is, they transmit the information at the same time using the same frequency band but using the different cores. Using the different cores, then that type of multiple access technique is called as CDMA. That is core digital multiple access techniques. And this CDMA is most commonly used in the satellite. And it does not mean that this CDMA and FDM frequency division multiple techniques are not being used, because there, like if we talk about the TDMA, the TDMA requires the bulky synchronization techniques, because ultimately this transmitter has to be synchronized with the time slot what is allotted at the satellite, and at the same time it should also be synchronized with that receivers where it needs to transmit the information. If there is even, since all these time slots are allotted in the millisecond or in the microsecond period, so if there is even very small change, variation in the actually this one time slot, then that will actually give the informations to another time slot, and that maybe received by another receivers, or that information may not be accepted by that time slot. Similarly, this if you type, so that is the main problem with the TTM. Similarly, there are some issues, important issues related to the FDMA also. But such type of synchronization techniques and synchronizations are not required in the CDMA. Only the possibility in the CDMA is that since the information may collide sometimes while transmission, during the transmission, some information may collide sometimes. So if that information may collide, then only the chance that the probability of error increases by a small amount. But at that time also that signal is getting received. And sometimes by sending the reverse informations to the transmitter, that is, that the information what you have transmitted is lost and retransmission is possible. And sometimes some error correction and detection scoring techniques are also being used to minimize the probability of error. So now, since these two you will be studying in the satellite communications, but here this also you will be studying the satellite communications. But since we are discussing about the applications of the DSSS, so it finds the very important applications in applications as a CDMA. Similarly, this CDMA is being used in the cellular telephony also. Okay, so we are going to discuss about the CDMA now. And in fact, the time is up and it is 3:20. So this CDMA I will be discussing in the next class. But just going to the, just giving you the basic definition of the CDMA, I will actually start our lecture over here. What is that? In CDMA, you can see in CDMA, each user is provided with an individual and distinctive PN code. As I told you, that in CDMA, they uses the same frequency band, at the same time they uses the same frequency band, but they uses a different codes. So, and how we provide the different code? Just by using our PN sequence, just by using our different PN sequences. So in CDMA, each user is provided with an individual and distinctive PN code. These codes are almost uncorrelated. This must be uncorrelated, because if that would be uncorrelated, then receiver will not be able to detect, able to identify that which transmitter has transmitted the information, that code, that signal. So this GI must be different for each user. These codes are almost uncorrelated with one another, and for the purpose of references, we are assume that sequences are indeed uncorrelated. Now, look to the first point. These things are already discussed. Consider that in the CDMA, consider that at given time, the things what I told you, that is at this particular given time, each number of K user is transmitting data at the same carrier frequency, because we are using the same frequency band. So they are using the same carrier frequency of mode. using the DS spectrum techniques. That is, different porting techniques are used. So which spreading spectrum techniques we can use? That is the DS spread spectrum. That's why I told you that this is nothing but an application of DS spread spectrum. And this particular code GIT, then each receiver is presented with the same. That I will discuss next time. Thank you. So if you have any questions, please ask me. Otherwise, we can stop our discussion over here. It is 3:24. Anyone of you, please.
No, sir.
So if you don't have any questions, then you are my leave. Thank you for that.
Thank you, sir.
Let us meet tomorrow at 11 a.m.